So let's start with a brief review of where we got to in the last video with this section summary. So we've got a curve, which is the red line here, and then we've got a secant, which is the blue line that cuts through the curve at 2 points and then keeps on going. And the chord, which is the line segment, which is starting at this point and ending at this point here. So they're the three words. And then we talked about the average rate of change for that curved line being effectively the gradient of the secant. So that gives us f of b minus f of a. So you can see that's the y coordinate y2 minus the y coordinate y1 all over b minus a, which is the x coordinate x2 minus the x coordinate x1. Okay, so that was where we left it, the average rate of change. And we saw this as, if you like, some kind of approximation of the gradient from point A to point B, or over the interval A comma B, if you like, as it says here. I'd like to take this to part 2 now. So I'm going to flick over to part 2 of our analysis task. And this was the gravity-fed water flow, where we approximated it with this curve here, where it was going quite quickly through the water to start with, and then as it finished filling up, it was getting slower and slower and slower. It was still filling up, but it was getting slower and slower and slower. And of course, our actual function would not, in reality, would not keep on going to here and then start going down again. That does not make sense, because once the container was full, it would not get fuller. Would not start emptying. So this rest of this curve is not part of the contextual domain. So it would be stopping after 70 something seconds or something like that. Okay, and that makes sense in terms of the table of values we've got here. And one of the questions that you had to do was you had to work out what the average gradient was over the first 50 seconds. And I'm going to express this as a line. So I'm just going to tick this so you can see it. This would be the average gradient that you would have worked out over the first 50 seconds. It's y equals 0.078x. That was my calculation. Your calculations will be a bit different because you had a slightly different function. That was just so, don't worry about that, other than the fact that I got the gradient by looking at the coordinates at 50, so 50 and 3.9. And then 50 divided by 3.9 rise over run gave me 0.078. And then I just treated that as a function, y equals 0.078x, which passed through the x axis, through the origin, and there we have our line. So that's the average gradient. So if the water flow was constant, then it would get to 3.9 litres at 50 seconds if the water flow was 0.078 litres per second. Okay, so that's basically what that means. But you can see it's such a rough average. It doesn't really describe what's happening over this time at all. It shows us the average, which is something, but it doesn't really describe anything here where the gradient is actually changing. It's variable all the way across. Then I asked you in that analysis task to then consider 25 to 50 seconds. So I'll turn that one off and turn that one on. There's the 25 second mark, 25,2.45 according to my graph. And then this one was fixed at 50,3.9 as it was before. And I think you'd agree that this graph here better describes this portion of the function. Okay, so we've got a better sense that this is a better approximation of the graph because it's closer to the curve, like so. I'll just turn this by, it's confusing if I leave it on for too long, but this one here, the curve is quite big compared to this line, but here, the curve is just over the green line here. So we would say this is a better approximation. And so the flow rate for me, or the gradient, was 0.058. So it's changed from 0.078 to 0.058. And you might notice here that the way I've got the straight line drawn, or the secant drawn, is simply by putting into y minus x1 equals m y minus y1 equals m outside of x minus x1, that particular notation, the point gradient form, to get that straight line. Nice and easy. So then the third thing you had to do is work it out over 45 to 50 seconds. So I did that again by using the 2 points, the point at 45, x equals 45, which was, if I just draw it up, there we go, bang. So at 45, we had 3.69, and at 50, we had 3.9. And we can see here, we can't even see the difference between the curve and the straight line here. So I have to zoom in a fair whack. And now we can see there's a bit of a difference here. We've got this point of intersection here and this point of intersection here, but it's really close to the curve. So I think we'd agree that between 45 and 50 seconds, this gradient of 0.042 is really, really close, really close. So as we get closer, a smaller and smaller interval for x, our secant is describing what's happening at the curve a lot more closely. So we've got 0.078 is a really rough approximation. 0.058 is a closer approximation of the gradient over that period or interval. 0.042 is an even closer approximation over that interval. And we can see there's a definite trend, 0.078, 0.058, 0.042. It's definitely trending towards 0.04 or thereabouts. So we can use our secants and our average rates over a very small period of time in order to determine or to estimate the rate of change at a particular point on the graph. The one we were going for in our analysis task was 50 seconds. So we could say that at 50 seconds, we would estimate it to be 0.04. Someone might say 0.039 or something like that. That would be a reasonable estimation as well. We could work out what the gradient was between 49.9 seconds and 50 seconds as well, and that would be an even closer approximation. So we can use these secant lines in order to get a closer and closer approximation. And as we see where the value is trending towards, we can set of the gradient, we can say that's probably what the gradient is going to be. And later on in our calculus course, we'll actually determine what the exact gradient is. So all of these are averages. And what we're trying to do is we're trying to work out or estimate the rate of change at a particular point, in this case, 50 seconds. This is the thing that we can't observe directly from the function. And so we need to estimate to start with until we've got a few more skills. So this idea of taking a smaller and smaller interval in order to determine what the flow rate is at that point is what we're at today. Okay, so we're looking at small intervals to estimate or approximate a gradient at a particular point on the graph. And when we look at the gradient at a particular point, as opposed to over 2 points, we call that the instantaneous rate of change. Okay, so the average is always taken from 2 points. Instantaneous rate is taken from 1 point. And over this next few lessons, we're going to be looking at how do we calculate as opposed to estimating that instantaneous rate of change. Because normally to get a rate of change of y over change of x, seems impossible when you've only got 1 point. But we know that rate of change must exist. So for example, when I'm traveling along the road, I might be speeding up, but I can look down at my speedometer at any time and get how fast I am traveling at that moment in time. So the idea of a rate of change at a moment does make sense, but we just need to know how to be able to calculate it. And the first idea behind how to calculate it would be getting these 2 points really close to each other and saying, well, this has got to be a decent estimate. So flicking over to the textbook, we're going to have a look at example 12. So as you can see here, instantaneous rate of change. I'm not going to talk about through these things here. We're going to go straight to example 12 so you can see how we might do it. And alongside, I might show you how this is done using your calculator as well. So a little bit of calculator usage. Okay, so example 12 says, consider the curve y equals 2 to the power of x. It says, using the secant through the points where x equals 3 and 3.1. This is what we were talking about before, using a really small interval estimate the instantaneous rate of change of y with respect to x at the point where x equals 3. So I can do that. I'm going to show you just a quick trick on how to do this on your calculator, just using your calculator screen as opposed to graphing anything. I'm going to define a new function. So I'm going to call it f1 of x. So that's just typed straight in. And now to define a function, I'm going to go control and then this button here. You can see it's a blue colon equals. That's how we define a function. And now I'm going to write the function in, which is just 2 to the power of x, like so. I'm going to press return, and you'll see it says done. Now, if I hit the var button here, you'll now see that I've got this function defined in, stored as a variable. And now I can use it. So it says we need to have it for between the points 3 and 3.1. We can see the instructions here. It says when x equals 3, y equals 8. When x equals 3.1, y equals 8.5742. The gradient of the line through here and here is 5.7419. And they did that just by using the average rate formula or the gradient formula. But I'm going to do it here so you can sort of see it. So it's going to be, if you remember, it's f of b minus f of a. So I'm going to go into here and create a fraction. And on the top of the fraction, I'm going to go f1 of 3.1 minus f1 of 3. So you can see f1 of 3.1 is going to be like the y2 value, and f1 of 3 is going to be the y1 value. And the x2 value is 3.1, and the x1 value is 3. So f of b minus f of a over b minus a. Press return, and I get 5.7418, blah, 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 which is the same as this value here if we go to 4 decimal places. So you'd say that would be the estimate for the instantaneous rate of change at x equals 3. Part B says repeat for the points where x equals 3 to 3.001. Now, one clever thing you can do if you want to is you can use your arrow keys here to go up to the question, press enter, and there it is again, all set out for you. Then you can use your arrow keys and you can now change it to what it asks you for, 3.001 minus f1 of 3, and then go down to the bottom and put 001 there as well. So again, we've got f of b minus f of a over b minus a, and that gets us even closer, 5.547, the same as the answer in the textbook here. So we would say that's a probably better approximation of the instantaneous rate of change at x equals 3, because we've done it over a smaller interval. And that's basically it. What you need to do is as many questions as you can from exercise 16D for the rest of this lesson, using exactly the same idea. Of course, they'll ask you different things or tricky things or give you intervals and stuff like that. But you need to interpret the question, and then you need to solve in a similar way, working out the instantaneous rate of change. So if we just have a quick look here at the learning schedule, you can see I've asked you to do exercise 16D, questions 1, 3, 5, and 6. So at least those, but the more you do, the better equipped you are for the rest of the week. So try and get through as many as you can.